Hello dear students and welcome to a new lecture on discrete mathematics. So we already learned about foundation of logic and proofs. Now we want to study basic structures. These topics are extremely easy and I'm pretty sure that already in your higher school you learn all these things very easy, but these are a part of the syllabus and we need to learn for programming. So under basic structures, we will study sets, set operations, functions, sequences, summation, and matrices. Sets are one of the basic building blocks for the type of objects that are considered in discrete mathematics. These are very important for counting, and also in programming language we have set and set operations. So set theory also is an important branch of mathematics. Many different systems of axioms have been used to develop set theory in mathematics. Here, we are not concerned with the formal set of axioms of set theory. Instead, we will use what is called as naive set theory. So in this lecture, we will study definition of set, describing set, important set in mathematics, empty set and universal sets, subset and set equality, cardinality of sets, tuples, Cartesian product, and later we will study set operations. Normally, sets are defined as an ordered collection of objects. As you can see in this image here, this is a set of geometric shapes, triangles, circles, squares, and hexagons, and so on. So the objects in a cell are called as elements or members. Elements or members. A set is said to contain its members or its elements. We use this in A in A. It means A is a member of A, is an element of A. And if it is not, we use A not in. It means A is not a member of A, right? For example, I am a member of Sejong University, right? But I am not a member of Seoul National University. So P, if P is me, P is in Sejong, but P is not in SNU, right? This is very simple. So sets are conventionally denoted with capital letters like A, as you can see here, B, C, something, and members are shown in small letters. In other words, a set is a well-defined collection of distinct objects. In mathematics, a well-defined set clearly indicates what is a member of the set and what is not. For example, the set of integers from -3 to 3, it means -3, -2, -1, 0, 1, 2, 3. Set of integers. On the other hand, we may say the set of lucky members. It is not well defined because it is open to interpretation. How you define lucky? There is no clear meaning of being lucky. These are not well defined. We cannot say. It is not clear from the description what lucky means, who lucky member will be considered, and what has to happen for numbers to be considered as lucky. There are any number of possible solution sets for here, so these are called as lucky. And later you will see that these are called as fuzzy. So here we have two types of sets. We can say crisp set and fuzzy sets. These are opposite to each other. In crisp, so it's here, crisp versus fuzzy. So when we say here the set of -3 to 3, for example, it's very clear which are there, well defined. But fuzzy sets are not clear. Let me give you an example. Here you can see the degree of body of human, right? So crisp. So we can define that if it is from 39.3 above, it means the guy has strong fever, and less than 1 has no fever, right? But it is not again well clear because from 39 to 40, the condition is totally different from 40 to 42, right? To 42, the guy will die. But in here, with some medication, it will go. Let me give you one more clear example. You say that this color is black or not, right? This color is black or not. And then you say this space is white. But let me ask you one question. This is white. This space is also 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 white. Do you think that in terms of color, all these whites are the same? Absolutely no. They are different, but we call them as white. So fuzzy says when you want to define something, you have to map it to 0 to 1, right? It means this color is 0 white, right? This is called as membership function, right? Membership degree. This here, to be a member of white set is 0. Here maybe it will be 0.7. Here it's maybe 1. Here it's maybe 0.6. Here maybe 0.9. Here maybe 0.2, right? So different. We can't say all are white because they are different. These two are called as, this concept is called as fuzzy set. Fuzzy set. Fuzzy set has been introduced by this gentleman, Lutfi Ezadeh. So he was a great man. He was known as the father of fuzzy. He was originally Iranian, but he grew up in the US from his bachelor. From his bachelor, he went to US. So, he had a lot of contribution in the fuzzy set. And, before neural networks become very famous, fuzzy was very, hot topic. Like in 2010 to 2010, fuzzy was much more famous compared to neural networks and deep learning. Let's see how to describe a set using roster method. The roster method is defined as a way to show the elements of a set. How? By listing the elements inside brackets. So we can simply say S, A, B, C, D. It means this is a set. And these are members. Order is not important here. A, B, C, D equals to B, C, D, A. Order is not important. For example, here, these are the same, or these are the same. These two are the same because A, B, C, D, A, B, B, and B, C, and C repeated, right? So the same. Each distinct object is either a member or it's not a member. Listing more than once does not change the set, right? So repeating doesn't matter. So we use ellipses like 3 points to describe a set without listing all the members, right? So for example, you know that A, B, C, D, E, F, G, H, something to Z, instead of mention all, just you use ellipses 3 points, right? Or you can say, for example, 1, 2, for example, 100. Here, example, sets of vowels in the English alphabet, A, E, I, O, U. Set of odd positive integer less than 10, 1, 3, 5, 7, 9. Set of positive integer less than 100, 1, 2, 3, 2, 99. Set of integer less than 0, from minus infinity to minus 1. There are some important sets that we all should be aware of them. The first one is natural numbers. Natural numbers contain all counting numbers. Counting means not 1 point something, 1, 2, 3, 4, 5, 6, 7. 0 is not included. If you want to include 0, then you should go for whole numbers. Whole numbers is shown by W, right? W equals to 0, 1, 2, 3, and more. It should be 3 points. Integers, the collective result of whole numbers and negative natural numbers. Minus infinity to plus infinity. 0 also included. Then we have positive integers, 1, 2, 3. 0 and negative are excluded. Then we have rational numbers. In the previous lecture, we talked about rational numbers. Numbers that can be rewritten as P divided by Q, and Q should not be 0, right? So these are rational numbers. Irrational numbers are the numbers which are not rational and cannot be written as the form of P by Q. These are called as irrational numbers. Then we have set of real numbers. So real number is the set of natural numbers, whole numbers, integer, rational, and irrational. All together will come here. You can say R equals to N, Z, and Q prime something. These are R. Then positive real numbers are more than 0. Also, we have complex number. A complex number is a combination of real number and imaginary. Imaginary means, for example, I equals to sqrt of minus 1. Example, like 3i something, yeah, 1.4i. These are here. So this shape shows the sets, natural, integer, relational. So it means from here to here, all are considered as real. From here to here, all are considered as real algebraic. From here to, so these are subset also. Later I will explain subset. Complex number, imaginary, and so these are important sets that we need to know. We use set builder notation to specify the property or properties that all members must satisfy. For example, S. When we say S, X in such a way that X is a positive integer less than 100. This is condition. This is the condition that X must satisfy. Condition. Or you can say property. Or attribute. Right? These are the, or we can say X is an odd positive integer less than 10, or x in this positive, right? Then odd and less than 10. We also may use predicates like this, s, x, p, x. For example, you can say s equals x in such a way that it's a prime x, right? This is a condition. We can use brackets, braces, and parentheses for describing sets. If this is bracket, it means a is included. If it is parenthesis, means a not included. You can say closed interval or open interval. When we say a to b, it means x equals to a and b. A and b are included in the set. When you say a bracket and b parenthesis, it means b is not included, right? Less than b. When a is start with parenthesis, a is not included. Then here a and b is not included. For example, when I say x less than equal to 5 minus 5. Minus 5 and 5 are included, both of them. It means it will be here minus 5, minus 4, minus 3, 2, 4, and 5. But in this case, when I write, so this is written as minus 5 and 5. This should be. When we say minus 5 and 5 in here, this one is not included. When I say minus 5 and 5, here minus 5 is not included, but 5 is included. When I say so this one should be like this. When I say minus 5 and 5, both are not included. The universal set, which is shown by U, is the set containing everything currently under consideration. Sometimes it is implicit. From the context, we understand that it covers all. Sometimes it's explicitly, but we mention the members explicitly. And content depends on the context. For example, the set of all Sejong undergraduate students. Here, I say the set of all undergraduate students at Sejong University. Right? This is a universal or set of all Sejong universities. Then we have empty set. A set has no element. We show by phi or this one. You should remember that phi is not equal to this. This is not empty set. This has one member and the member is phi, right? So these two are not equal. For example, the set of undergraduate student who holds PhD degrees, empty. To visualize sets, we use a Venn diagram. For example, here I show a set of letters in English. So this is English. This is English. Latin, for example, this is Latin. And Russian, this is Russian. So these three sets have some common parts. This area is common between L and R. This space is common between E and R. This space is exclusive for R. This space is exclusive for R. This space is common between E and L, and this space is exclusive for L. Sets can be elements of other set. As you can see here, we have one set. This set contains another set, and a member. So if we say, for example, A equals if B equals 1, 2, and 3, and C equals B and C, then we can say A equals B, set B, A, and C, right? Or you can see here, this is a set of a big set which contains different other sets. What is that? Natural numbers, integers, rational numbers, and real numbers. A big set contains 4 other sets. Here is a definition of set equality. Two sets are equal if and only if they have the same elements. A equals B if and only if for all x is in A and both sides, right? X in B. It means x should be in both of them. For example, 135, 351. Order doesn't matter. In here, 1, 5, 5, 5, 3, 3, 1. 1, 3, 5, same. Or repetition doesn't matter. Members are there. We have a definition for subset. The set A is a subset of B if and only if every element of A is also element of B. We show like this, A subset of B. We say A subset of B holds if and only if for all x in A, it gives x in B also as well. In here, it is not by direction. It means there may be some elements in B which are not available in A. If it is like this, it means two sets are the same. This is B, this is A. in here some set, some element, in here some element. This element is in A and also in B, but this element is in B but not in A. Based on the definition, phi or empty set is a subset of S, right, for any. And also S is a subset of itself because every element is there also. We want to see how to show a set is or is not a set of another one. To show that A is a subset equal of B, if X belongs to A, then X also belongs to B. And here, to show that it's not a subset, we use this symbol and we say that we find an element in X in A, but it is not in B. So in here, such an X is a counterexample to claim that X is in A, but is not in B. We can use logical equivalences as we learned already, like we have if A equals to B, if and only if for all X, X is in A, implies X in B, and X in B implies in X in A. It means same, right? Same. As you can see, A is a subset of B and B is a subset of A. It means A equals to B. For example, the set of all computer science major at your school is a subset of all students. Yes, this is correct. The set of integer with score less than 100 is not a subset of the non-negative integers. Here is another definition of proper subset. If A is a subset of B, but A is not equal to B, then it is called that A is called that proper subset of B. And we show like this. It means they are not equal. So if A is a proper subset of B, then for all X, X in A give to X in B, and there exists X in B and not in A. This is called as counterexample. I give you already example here. This is a universal set. Universal set. Then there are some elements in B and there are some elements in A. Each element of A belongs to B, but there are some elements in B which are not element of A. This is called as proper subset. Here is the definition of set cardinality. If there are exactly n distinct elements in S and n is non-negative integer, we say that S is finite. Otherwise, it is infinite. Cardinality of a fine set, which we show like this, is the number of distinct elements of A. The cardinality of phi is 0. This is empty list. Empty set. Cardinality of phi is 0. If S is the letter of English alphabet, the cardinality of S is 26 because there are 26 letters in English alphabet. The cardinality of a set 1, 2, 3 is 3. The cardinality of this is 1. The cardinality is this one is 0. But here we have a set inside this one. This is 1. Then this is 0. The definition of power set is represented here. The set of all subset of a set A, which is denoted by PA, is called as power set of A. Here we have example of A equals to A and B. The power set here. Phi already we show that empty set is subset of any other set. This can be 1, A, B, and A and B. So 1, 2, 3, 4. There are 4 power sets for A. If a set has n elements, then the cardinality of power set is 2 power of n. The order n tuple, like A1, A2 to AN, this should be AN, is defined as the order collection that has A1 as its first element and A2 as its second, and so on, so to A of n. When we say ordered pairs, it means 2 n tuples. 2 n tuples are equal if and only if their corresponding elements are equal. So 2 tuples are called as ordered pair. For example, the ordered pairs A and B and C and D are equal if and only if A equals to C and B equals to D. So you can see here for empty list is 0, for 1 is empty and 1, 0 and empty 1, phi or 1. 1 and 2, 1, 1 as a set and 2, phi and 1, phi and 1 and 2. So these are the ordered tuples. René Descartes, he proposed a Cartesian product. The Cartesian product of 2 sets, namely A and B, is shown by A multiplied B, and it's the set of ordered pairs of A and B, where A in B A and B small is in B capital. So we show that A Cartesian product of B is A and B in such a way that A is in A and B is in B. For example, if we want to find the Cartesian product of A and B as one set, 1, 2, 3, and one set, what we do? A and 1, A and 2, A and 3, B and 1, B and 2, B and 3, A and 1, A and 2, A and 3, B1, B2, and B3. This is called a Cartesian product. For each element in the first set, all elements of the second set are repeated. A subset of the Cartesian product is called as a relation. So this is called as relation. And we have not only for one, we can have many, right? Like A to N multiply A to N, right? So for example, you can see here, if we have A, B, C, like A 0, 1, B 1 and 2, and C and 1 and 2, we want to do Cartesian product. 0, 1, and 0. This is 1. 0, 1, and second one, 1. 0, 1, and 2. This is finished. 0, 2, and 0. 0, 2, and 1. 0, 0, 2, and 2. Finished. 1, 1, and 0. 1, 1, and 1. 1, 1, and 2. Finish. 1, 2, 0. 1, 2, 1. 1, 2, 2. Finish. This is called as Cartesian product. All right. So here we want to talk about set operations, which are somehow Boolean algebra. Propositional calculus and set theory are somehow instances of algebraic system, which we call it as Boolean algebra. So the operators in set theory are analogous to the corresponding operator in propositional calculus. As always, there must be universal set like U, and also all sets are assumed to be a subset of U. So in this lecture, we will study some basic, I think already you know all these topics, but just it's our reminder to you, like union, intersection, complementation, difference, set cardinality, and set identities. Somehow we already studied them like in algebraic and propositional calculus, but here we will study in terms of sets. Union, if we have two sets like A and B as two sets, then the union is denoted by A cup B, and it is defined as all x's in such a way that x belongs to A or x belongs to B, right? And also we show using Venn diagram, if this is our A and this is B and this is the universal set, then union of A and B is total of this area. For example, if we have two sets, the one is A, for example, is 1, 2, 3, and B is 3, 4, 5, then the union of A and B is 1, 2, 3, 4, 5, right? As you can see here, if this is A and B, then union will be all of them. Intersection is corresponding to the AND operator. So if you have again two sets of A and B, and in here we say all x's which are belongs to A and B, right? Both of them common. You can say common parts. If we have two sets 1, 2, 3 as A, for example, and B as 3, 4, 5, A cap B is 3 because only 3 is common here. 1, 2 are not available here. 4 and 5 are not available in the first one. So the common part is only 3. Another example, if for example this is set C 1, 2, 3 and another set D 4, 5, 6, then C cap D is what? There is no common element. That's why it is empty or 5. And here this is the Venn diagram for A cap B, and the common part is only this part, okay, not all. Intersection. The next terminology is complement. If we have again a set of A, if this is our set of A here, and if this is universal, then the universal minus A is the complement. Or you can say any member which is in universal but not in A. We can show by this one a complement of A, right? So we can say for all x's in A but are not in U but are not in A. This is called as complement of A. For example, if the universal set is positive integer less than 100, what is the complement of x in such a way that x greater than 7? So less greater than 7. Greater than 7 is our A. This is considered as A, right? Universal is less than 100. So you can say universal is positive integer less than 100. 1, 2, 3, 2, 99, right? A is greater than 70. 71, 72, 72, up to 99. Then complement of A equals to what? This one minus this one. 1, 2, 3, 2, 70. Very easy, right? Difference The difference of A and B, which we show by A minus B, is the set containing the elements of A that are not available in B. Because here is a common part, so we have to exclude this part. Then we say that X are in A and X not in B. It means we can say that A minus intersection, right? Or you can say intersection of A and B not, right? Here is an example. If our universal set is 0 to 10, A is 1 to 5, and B is 4, 5, 6, 7, 8. Then A cup B. A cup B or A union B is what? It means all A and B. 1, 2, 3, 4, 5, 6, 7, 8. A cap B or A intersection B means common parts. A is not here cut. 2 is not here cut. 3 is not here cut. 4 is here. Okay, 4 come here. 5 is here. Then only 4 and 5. A complement means universal minus A. So 1, 2, 3, 4, 5, 0 and 6 to 10. A minus B, right? A minus B, universal. Then we can say that 0, 1, 2, A minus B. It was wrong. A minus B means all the nodes, all the members which are in A but not in B. For example, 1, 2, and 3 are in A but not in B. 4 and 5 are in B, so it will not be included. The otherwise is the nodes, the elements which are in B but not in A. We don't have anything, so it is empty. B complement means the elements of universal which are not in B. 0 should be here also. 0, 1, 2, 3, 4, 5, 6, 7, 8 are there, 9 and 10. So 0, 1, 2, 3, 9 and 10. This is complement of B. The symmetric difference of A and B, which we show by plus circles, this is called as plus circles. Plus circles of A and B is called as symmetric difference, and it is A minus B union B minus A. This part and this part. You can say union minus intersection. Union minus intersection. So if we have a universal set as 0 to 10 and A is 1, 2, 3, 4, 5, B is 4, 5, 6, then symmetric difference of A and B is sum minus common. 1, 2, 3, 6, 7, 8. Common is 4 and 5, right? These two should not be included. 1, 2, 3, 6, 7, 8. These two should be excluded. So we have some set identities like the laws that we already learned. Here we show by cap and cup. The identity law means A union of empty is A itself. A intersection union is A. A union U is U. A intersection phi is phi. It means because they have no common elements. A and nothing, no common elements, right? Nothing. Then we have idempotent law. A union A is always A, and A intersection of A is also A. Complementation law say the complement of A is A. The complement of A is A. Then we have commutative law. It says A union B is equal to B union A. It doesn't matter if you change, and the same thing is applied for intersection. A intersection B equals to B intersection A. In the associative law, if we have three sets, we can do changing the parentheses, the priority. A union B union C is equal to A union B union C. A intersection B intersection C equals to A intersection B intersection of the result with C. Then we have distributive law. In here, A intersection of B union C equals to A intersection B union of A intersection C. And A union of B intersection C equals to intersection of A union B and A union C. The Morgan law is applicable here also when we have complement on union. It will be intersection of complement individuals. And the same, the complement of a intersection is union of complement of two sets. Then we have absorption laws. A union of A intersection B is A. So in here, we will bring the members which are in B, not in here, not in A. But then we say union, right? Intersection of that part. You remember here, if this is A, if this is B, right? A intersection B is this part. A union of intersection means whole A, right? And the same is applicable for this part. Union of A and its complement is U. If this is our U and this is A, then this part is its complement. So A union complement is U. A intersection with its complement is nothing. So we have different ways in order to prove set identities. We can use proofs at each set. Side of the identity is a subset of the other. We can use set builder notation and propositional logic, and also we can use membership tables. We will see many examples. Here is one example. A intersection B equals to B minus A. So we want to prove this one. So we can use this one using different methods like set identities, membership tables, and the other things. Here is what we are going to prove. We want to prove this one. This is shown in Venn diagram. We want to say that A intersection B is this part. On the other side, B minus A is this part. Then whole B minus A is again this part. So we want to show that these two are the same. So you can use basic set identities. We start from here. A intersection B equals to B minus A. We can write B minus A as B intersection of A complement. B minus A. Let me draw the. If this is A, this is B, and this is universal. So B minus B intersection of complement. B intersection of complement. A complement is this part. Right? This is A complement. B intersection with B complement is this part. Same, right? Then we can write this part as B intersection with complement of this one. Complement of this one is the rest, right? Using the difference definition that we have. Then this can, using the Morgan law, if you remember, the complement of something will change the, if it is union, it will be intersection. If it is intersection, it will be union. So this one will be rewritten as this one. So if we apply this complement, this intersection will change to union, B will be changed to B complement, and A complement will be complement of complement. Complement of complement is A, right? Is A. So this one will be rewritten as this one. Then we have B intersection of union of B complement and A. Okay, this can be rewritten as, based on distributive law, we can write it as B intersection of B complement union B, one time with this one, one time with this one. B intersection with A. This is using distributive law. Then intersection of any set with its complement is phi, right? And the rest is the same. Then using identity law, we say that union of any set with phi is itself. So phi will go out. Then this will come here, and simply we can write B intersection of A is equal to A intersection of B. Then, so we proved. So here is our original statement. We say that X in such a way that X is in B and X not in the difference part. Okay. Then we can change this part to this. X in B and negation of X in. So this not in is equal to negation, right? Same. So just we change it. Negation of X in difference. Then using difference, we can write that this part is the same, that negation of X in B inverse, it means this difference can be rewritten as this one. X in B and X not in A. This is the meaning of difference we have already. Then we can change this one, apply the negation. If we apply the negation here, X in B will be X not in B and will be changed to OR, and X not in A will be changed to X in A because we apply the negation, or you can say the Morgan law. Then based on distributive law, we will apply X in B and X not in B or X in A. We apply this one time with this, one time with this. X in B and X not in B, or X in B and X in A. Then using negation element of, we apply this one. X in B and not X in B, same, right? As I said here. And X in B and X in A, same. Then X in B and X not in B is false, right? It's false. And the rest is the same. Then we have this one, or F is always itself, and this is the meaning of intersection. So in this way, we proved it. Here is another example. Prove that complement of intersection of A and B equals to union of complement A and complement B. We prove this identity by showing that complement of A intersection B is a subset, A complement union B, and A complement union B complement is a subset of A complement of A intersection B. So by assumption, we have x in complement of A and B. We can change it by complement, that when we say this is in complement, it means it is not in itself. It is not in A intersection B. Then by the meaning of intersection, we say that it means, this one, it means x in A and x in B, negation of x in B and x in A. Then based on the Morgan law, it means x in A. So this one, we apply this to these elements. Negation of x in A or and has been changed, and negation of x in B. Then we apply again negation of x and A. It means x not in A or x not in B. So x in not in A, it means x is in complement of A, and x not in B, it means x in complement of B. And based on the union, we can say x is in complement of A union complement B. Then we show that complement of A union with complement of B is a subset of or equal to A intersection B complement. So by assumption, we have this one. Then union x in A complement or x in complement of B. Then we change the complement. It means x is in complement E. It means x is not in A. X is in complement of B. It means x is not in B. Right? Then again, say we apply the negation here. We apply based on the Morgan law. We apply to A and B. Then the negation come outside, and finally we will come with complement of x. When we say negation of x in intersection of A and B, it means x is in the complement of intersection A and B. So simply we can prove it. So the same definition with set builders notation. So in here we say, when we say complement of A intersection B, it means x is not in A and B intersection B. This can be written as negation of x in A intersection B. Then we apply the negation. When we say x in A intersection B, it means x is in A and x is in B, and we have a negation here. Then we apply the negation of x in A, or this has been changed because negation is there, and negation of x in B. Then again we apply negation of x in A is x not in A, and negation of x in B is x not in B. We have or here. Then x not in A, it means x is in the implement of A, and x not in B, it means x is in the complement of B. Then we can write that x is in A complement union B complement. Then this can be simply rewritten as this one. So we can use the set builder to prove it. And also in there we have truth table. In here we have membership table. The same way that we show. So we have A, B, and C. We have A, B, and C here, right? Because parenthesis has the priority, so B intersection A, the same. B intersection A, 1, 1 is 1. 1, it's like end. It's like and 0, 0, 0, 1, and the rest is 0. Then A or B and C. So this one with this one, or this one is 1, this one is 1, this one is 1, 2, 0, we have here 0, and the rest is 0. Then we have, so this is one part. Then we have A or B. A or B is this one, A or C is this one, and A or B and A or C. A or B and A, C. So this is and between these two. So you can see that these two are the same. We prove this equality using membership table. So we can use generalized union and intersection for many sets instead of 1 or 2 sets or 3 sets. Here you can see we have 1, 2, up to n set, 100 set, 200 set, 1000 sets, right? So then we use this notation. Instead of A union B, we use this one. It means we have n sets from I to NAI. It means A1, A2, A3, A up to AN. And the same thing we can use for intersection. It means the intersection of n sets. Okay. So for example, if our I is 1, 2, 3, 4 something, then AI, it means I plus 1, I plus 2 something, right? So you can see here union of I to n sets. It means I plus 1, I plus 2, 1, 2, 3. And the same thing is for intersection. Generalization means we have many sets instead of 1, 2, or 3. Then we have the concept of bit string representation. Bit string representation, for example, for the length of n is like bitwise that we had already. So AI if x is in the set and 0 if it is not there. Okay. Let's see the example. If this is our universal set and this is A. right? This is universal, this is a set A. Then how we represent A in bit string representation? Very simple. X1 is available, yes, 1. X2 is not available, 0. X3 is available, the next one is X3, right? Available, 1. X4 not available, 0. X5 available here. X6 available here. So we just compare our set of A with universal. If the corresponding element is available in A, we show it using 1. If it is not available, we show it using 0. Very simple. Here is an example. If our union set is like this, U equals to X1, X2, X3, X4, X5, and X6. And 1 is 1, X1, X3, X5, X6. B is X2, X3, X6. We want to do bit operation. So how to represent A in bit? 1 is available? Yes, 1. 2 is available? No, 0. 3 is available? Yes. 4 is available? No. 5 is available? Yes. 6 is available? Yes. This is 1. For in case of B, 1 is available? No. 2 is available? Yes. 3 is available? Yes. 4 is available? No. 5 is available? No. 6 is available? Yes. How to do bitwise OR? This is bitwise OR. 1 and 0, 1. It is OR. 0 and 1, 1. 1 and 1, 1. 0, 0, 0. 1, 0, 1, 1, 1, 1. And end. 1 and 0, 0. 0, 1, 0. 1, 1, 1. 0, 0, 0. 1, 0, 0. 1, 1, 1. This is bitwise AND and bitwise OR. That's all. This was simple introduction about sets and set operations. I know the concept was very easy, but this was just a reminder for you that we later use in our programming assignments. Okay, thank you, and please feel free to ask me if you have any questions.